Okay, so we are looking at note 3.5, and we're dealing with rational functions. Now, we dealt with rational expressions and rational equations, but now we're going to look at functions and we're going to be graphing them. Okay, so what is a rational function? So a rational function, as we kind of remember when we talked about rational expressions and rational equations, the word ratio in there tells us that it's going to be a ratio or a quotient of two different functions. So f of x is our function, and it's going to be a ratio of two other functions, or polynomial functions, really. So, and that means that we're talking about a quotient or a ratio of polynomial functions is what we're going to use to make up our function. All right, now this causes us some problems because there are going to be times and certain values of x that will make this denominator equal to 0, and that's bad. We know we cannot divide by 0 in mathematics, so we would have to remove from the domain any value of x that would cause f of x to be undefined, and that's going to be when h of x is equal to 0. And so at that particular x value, we're going to have some kind of break, or we will sometimes refer to it as a discontinuity, or the function itself will be discontinuous at that particular x value. So let's look at an example. So starting with a pretty simple example of 1 over x. Now to start with, we'll make sort of a table, but we won't really be using big long table like this for most of our functions. Probably in most cases we will be able to get away with just 4 points. All right, but just for the sake of being thorough for this very first graph, let's use these x values, and when we plug those in, what do we get? So we put in negative 5, so it'd be 1, 2, 3, 4, 5. So a negative 5 value. What will the y value be? It'll be negative 1 over 5, so negative 1/5. All right, so that'll be, let's say, about here. Okay, and then negative 2, so that's here. Negative 2, that will be negative 1/2. And so negative 2, negative 1/2, that'll be about here. And then if we do negative 1, the reciprocal of negative 1 is negative 1. And then, negative 1 here. And then if we do a half, negative 1/2, that will be negative 2. So if I go over to negative 1/2, I'll be down here at 2, negative 2. And let's say we go over just a 1/5, that'll be down here at 5. So you can see there's kind of a nice, almost a symmetry to this. So that'll be negative 5. And what happens if I put in 0? Well, that's undefined. Right? So we can't plot that point because it makes our function undefined. All right, so let's go and try some positive things then. So what about 1/5? That would be 5. So up here. And if I go over a half, that'll be up at 2. If I do 1, it'll be 1. 2 will be a half. And 5 will be 1/5. So you could see not only is there a nice symmetry here, there's also a symmetry about the whole thing. So let's kind of sketch what that would look like then. So and you can see here that we can't put in 0, but we could put in something really close to 0. So as we get closer and closer to 0, say from the positive side, let's say we put in a 1/10 for x. Well, then our value is going to be up at 10. If I put in 100th, right, so 0.01, then it's going to be up at 100. So you can see that this thing explodes almost, going vertically. And it does the same thing in the negative direction as we approach 0 from the negative side. And so at this undefined value of 0, we will have what we call a vertical asymptote. So we often will dash in a line instead of making it solid because that confuses us with the axes. So we'll put in a dashed line for the asymptote. Okay, so there's a vertical asymptote at that x value that would have made the denominator 0 and the function undefined. Okay, so let's see. Let's answer some questions over here. So this function decreases on what interval? So on the whole interval. So starting on the negative infinity, going all the way down, not ever getting to 0, but really close, negative infinity to 0, non-inclusive, because of course that would make it undefined. And then on the other side, this whole thing is decreasing as well. So we would say from not 0, but not inclusive of 0, 0 to infinity. So for the whole domain, under its whole domain, it's decreasing. All right, the function is discontinuous at an x value of 0. Has a vertical asymptote at x equals 0. It has a horizontal asymptote. Notice now it has a horizontal asymptote here. As x gets really big, right, it's never going to be equal to 0. The y value is never going to, it's getting closer and closer to 0, but there's no way that 1 over x could ever equal 0, right? If x gets really, 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 really big, then the whole value gets smaller and smaller and smaller and approaches 0. So we have a horizontal asymptote here in this case at y equals 0. All right, and then just to think about, there's symmetry here. There's not a reflective symmetry, but there's a rotational symmetry, right? If I flipped it about the origin, it would look just the way that it did, right? So that tells us that this is odd, all right? It's symmetrical about the origin, so it is an odd. Okay, the reciprocal function can be thought of as the parent. And then these functions all are sort of versions of that, transformations of that. So if you think, we could take, if this was the parent function, then what's 2? Well, that's like 2 times 1 over x. And then this minus 1, that's a transformation. That's going to shift it. Remember, if we thought of it as like almost like a parentheses here, instead of x, we're putting in x minus 1. That shifts it in the opposite direction to what you think. So instead of the asymptote being at 0, it shifts over to the right one. So here the vertical asymptote, which makes sense because what x value would make this denominator 0? 1, right? And so notice I'm putting it in as dashed so that I don't confuse it with the y-axis. Okay, and then the 2 tells me I'm just taking all these values and stretching them. So instead of we're going like, think about here. This is the center, sort of the center of our graph, right? We're going to move that over 1. This is not translating up and down. It's stretching it up and down with that 2 out in front. So the horizontal asymptote is still staying the same. So if we think about from this, not the origin, but the center of where the asymptotes meet, if I went over 1, I would go up 1. That's what we did here, went over 1, up 1. But here we're going to go up 2 because of the stretch. All right. So if I was at a half away, I would be at 2, but now I'm up at 4 because of that vertical stretch. Okay. So then if I was over here at 2, I would normally be at a half, but again, because of the vertical stretch of 2, I'm going to be up at 1. All right, and then the same thing happens with these things down here, over here. So instead of being over 1, down 1 from the intersection point of the asymptotes, I'm going to be over 1, down 2. And then instead of being at a half, at a half, I would be down 2. I'm doubling that to 4. And then over here, if I went over 2, I'd go up a half, but I'm doubling it to 1. All right. So we could just kind of sketch those in. And so these asymptotes, all right, so I talked about these asymptotes. So it's a line that, that the curve is going to approach infinitesimally close. It's going to get closer and closer and closer. As my x gets closer and closer to 0, this curve is getting closer and closer. It never touches, never crosses, never swings back away from, but just keeps getting closer and closer to it. And so in mathematics, that kind of a line, that's what we refer to as an asymptote. So we talked about, I mentioned it up here, but we didn't really talk about what it is. So the same thing for horizontal asymptote, same kind of thing happens. This curve is getting closer and closer and closer to that horizontal asymptote. It never touches it, never crosses it, but just gets closer and closer and closer to it. Okay, so that's what this graph looks like. All right, so now let's think about what this graph looks like. What x value makes this function undefined? Well, that would be -1, right? So we'd be going back in this direction. And if we didn't have the 2 on it, that would be it. The horizontal would be at 0 still. But here with this +2, we're moving up. The horizontal asymptote gets moved up. Okay? So, I mean, think about it. If x gets really, really big, then 1 over x plus 1 is also very, very big. But 1 over that is really, really small. So it's close to 0. But we're adding 2, so it goes up, okay? There is no stretch or shrink here, so we could, the same relationship that these points have to this intersection of asymptotes is the same that happens here. So I could very quickly plot some points, half and a half and 2.5, over a half down 2, over 1 down 1, over 2 down a half. So I could plot those points very quickly, and that's the whole idea of, this parent function. If you know what the parent function does, then these will do the same thing. There's no stretch here. It's all going to be just a translation, right? So from the origin, it switches over 1 and up 2. So the x plus 1, that's always the opposite of it. So it went to the left 1. And then it went up 2 because of that. All right, so let's think about what this one looks like. So we have a negative in front, so that means the whole thing's going to flip. So instead of being down here and up here, it's going to be here and here, like, in this one. But let's think about the asymptotes. 0 will make this thing undefined, so we got to have a vertical asymptote here at an x value of 1. And then if x gets really, really, really big, this part goes to 0, but then we have -1. So our asymptote, horizontal asymptote, is going to shift down. Okay, so the horizontal's at a y value of -1. The vertical axis is at x equals 0. And then there's no stretch or shrink here. So it's still the same relation, only we've got that flip thing. So instead of going over 1, up 1, I'm going to go over 1, down 1, and then the reverse here. So over to the left and up, and then, a half 2, -2 a half, going over 2, down a half, going over a half, down 2. And these are all in relationship, instead of from the origin, it's from the intersection of the two asymptotes. So something like this. Now, when you're drawing these, we don't want to really touch that asymptote. So I would say do something like that. Draw a little arrow to kind of indicate. You want to sort of, I guess, show, maybe I should have gotten a little closer, show that that's an asymptote and it's getting closer and closer. But don't touch the asymptote. Don't cross the asymptote. All right. All right, so same kind of thing here. We have this -1. That's going to flip it like this one did. Think about where the asymptotes are. That'll help us kind of guide where this is going to go. X plus 2, so that's going to shift to the right 2. Vertical asymptote's going to be here. You could also think of it like, all right, what x value makes this undefined? clearly, oh, sorry, I went the wrong way. Negative 2 should have been here. So that's negative 2 will make this thing undefined, right? Make it 0, and the whole thing would be undefined. And then the plus 1, that's going to move it up 1, so our horizontal will be here. And again, the negative is flipping it, so it's more like this, but it's the same relation as these are to this point as they are to this point in this graph. So I'm going to go from the intersection, I'm going to go over 2 up half, over 1 up 1, over a half up 2. And then the same things repeated down here. Okay, and then we'll sketch our graph in and just, draw arrows before we get too close. It's a little hard to draw because this is kind of small graph paper, but something like that. Okay. So if we know what the parent function looks like, these are pretty easy. We don't have to make a bunch of points. Generally 2 on either side. In this case, we went ahead and just did 3 on either side. We didn't have to make a table, though. The whole idea of the parent function, if you know what it's doing, then if we understand how these transformations occur, then we can graph those without making a table. All right, let's look at another function. This is 1 over x squared. And so let's plug in some values. When I plug a 3 into this, I get a plus or minus 3. I get a 1/9 because we're squaring it, so the negative would go away. So let's say 1 to negative 3, and we're at a 9th. So pretty close to the line, pretty close to the line here. Pretty close to the x-axis, I mean. And then if we put in a negative 2, that's going to be 1/4, positive or negative, 1/4. So a little higher, but still pretty close. And then when we plug a plus or minus 1 in, we get a positive 1. So let's put that in here. And then if I put a half in, that will be 4. So a half, it jumps up 1, 2, 3, 4. And at a positive a half also, at positive and negative 1/2. And then at 1/3, so positive, negative a third, that jumps up, and that's going to be 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So a third and a third. So you can see you can't put a 0 in. If I put a 0 in, I get it's undefined at 0. So I can't put a 0 in, and you can see that has an asymptotic effect on it as well. And as you can see, we also have an asymptote here at x equals 0. If we plugged in a couple bigger values, say we plugged in 5, it would be a negative 5. We would have what 1/25. I mean, really close, right? So close that we couldn't really. I mean, the line thickness is probably as much as a 1/25. So something like that is what we should do. And then just kind of draw in arrows once you kind of get past those points. All right, so it's decreasing on what interval? It's decreasing from 0 to infinity. It doesn't ask, but it's increasing on the interval of negative infinity up to 0, but not including 0, right? Exclusive of 0. So it's going up. It has this asymptote here at an x value of 0, and then also here at a y value of 0. All right, function is discontinuous at an x value of 0, has a vertical asymptote at x equals 0, and a horizontal at y equals 0. All right, this one is not odd, but instead it is actually even. And then we could do a similar thing with this, and do transformations just like we did up here for these 4. We could think of this as the parent function as well.